In this lecture, you will learn about fundamentals of radio detection and ranging, or radar, and some of its applications. The history of radar is quite long, starting with James Clerk Maxwell, that in the 1860s presented the theory behind it. However, it was not until the 1960s and onward that the more modern version of radar emerged, and it's only in the last few decades that radar has moved into the mass production in the automotive industry. These images are from Autoliv development of radar units for the automotive industry, together with Celsius Tech in the 1990s. It was in the 1990s that the first premium cars were fitted with radar-based adaptive cruise control. Radar typically provide three measurements. First, range, which is typically provided in meters and is given by the time it takes from a signal is sent out until it's received again, but also phase information can be used. The second measurement, relative speed, is provided by Doppler, which is the frequency shift in the signal due to the relative speed of the own vehicle and the measured objects. Third and finally, the angle of measurement objects in relation to the own vehicle. For the angle, there are different techniques, where older radars use moving antennas, while modern radars typically use a set of antennas. That is, the radar then transmits a diffuse widespread signal. The multiple receiver antennas are then used to calculate the angle in post-processing, taking into account timing and phase, etc. There are many tricks in designing good radar sensors, and many have to do with how to do good frequency and amplitude changes in the best possible way to provide as good range, speed, and angle measurements as possible. Older radar sensors use only the time of flight in their measurements. However, modern radars often transmit, for example, continuous changing frequencies. By comparing or blending the incoming and current ongoing frequency, the range can indirectly be calculated. Different techniques have different benefits and drawbacks. With changing frequencies, it can be a challenge to disentangle the Doppler frequency shifts of the relative speed in the incoming signal from the original frequency shifts. But on the plus side, it enables the measurements of static objects. As always, both performance and cost strongly affects the design choices. As radar costs are reduced, they are also used more and more in cars and trucks, not rarely as standard equipment, and for a very large variety of applications. Applications of radar range from pure forward-looking radars, facilitating adaptive cruise control, forward collision warnings, and automated emergency braking systems, but also backup alerts, lane change assists, and even safe door opening applications. There are today quite a few radar sensor suppliers competing on the automotive market. The list on the right shows some of them. Different radars use different frequencies, 24, 77, and 79 GHz. Most modern radars use the higher frequencies. 24 GHz are limited in transmitting power, but have also low bandwidth, and also have lower costs and lower tolerance requirements. 77 and 79 GHz radars are smaller devices and have a wider bandwidth. Bandwidth affects, for example, the distance resolution and accuracy. When designing a radar with respect to resolution, both signal-to-clutter ratio and the signal-to-noise ratio should be taken into account. For the former, optimizing the resolution in the detection space of range, speed and angle, and for signal-to-noise ratio, optimizing the time on target and use bandwidth. Note, as mentioned in an earlier lecture, that compared to, for example, LiDAR and vision systems, the angular resolution for radar is typically significantly worse, due to the intrinsic designs of radar versus the other two sensor types. An object's reflection is typically quantified by the cross-sectional area of a perfectly reflected sphere that would produce the same strength as a reflection as the object would do. The area metric is typically noted sigma. A truck may have 10 times the reflective area as a car, which may have 10 times the cross-sectional area of a pedestrian. However, due to different reflectivity, a mailbox can have the same radar cross-section as a car. The reflection is further often moving around on an object. At one angle, the rear of the car may be reflecting the most. In the next moment, for example due to the vehicle head turning, large reflections may instead come from one of the wheelhouses. The cross-sectional area is also frequency dependent. For example, a 1 square meter at 24 GHz can be the equivalent of 10 square meters at 77 GHz. Reflections on guardrails and other vehicles can produce ghost objects. Methods for identifying and suppress ghost objects need to be taken care of when using radar in actual applications. This was a short introduction to radar sensors. Radar sensors are key to many automotive safety applications and are now reasonably inexpensive for use in a multitude of different automotive applications. Radar sensors are therefore not uncommon as standard equipment in modern cars. Thank you for your attention.